So if we're talking about poles and zeros, poles are the roots of the polynomial on the bottom of the transfer function, the polynomial in the denominator, which we label q, and zeros are the roots of the polynomial on the numerator, the one we label p. The zeros give us critical frequencies, these will be interesting to us when we look into root locus, and then also when we look at Bode plots. And the poles give us the system stability. Okay. All right, so indeed, if you want to look at the stability of an entire system, you'd be looking at GCL of S, that closed loop, that entire system, and then you would be examining the QCL that is on the bottom, the denominator polynomial right there. If you solve for the roots of this, you will get your poles, which then, if all is good, everything's in the left-hand plane on that complex plane. And that's what we are looking for. So we graph the poles out here. And the zeros, when we graph them with respect to root locus, let's say they are circles like that. If we have 3 out here, just like that. Poles are x's, zeros are circles or zeros. Okay. And so what you want to be looking for is, well, you know what? Let's look through a couple of examples of stable systems. And this is covered in another video more, but we'll just do like 2 examples real quick. So let's say a stable system. Okay, so let's say we have a g of s. We'll say a g of s1 equals, say our polynomial on the top, we have something, we factor it out, and it is this right here. And then on the bottom, we have an s plus and an s plus 10. We'll make it pretty stable. Okay, how can I tell if this is a stable system? I want to inspect the polynomial on the bottom. I want to inspect the poles. So here I have s plus 100. If I solve that, I set it equal to 0, I get s equals negative 100, and this represents my pole. This is actually one of my lambda sub I. Same thing with this. S plus 10, set it equal to 0. I have an s equal to negative 10. That is also one of my lambda sub I. So out here, indeed, I'm actually here at negative 100 and negative 10. Okay. Our zeros in this case are not plotted correctly. I would have a 0 that is over here in the positive plane and one that is in the left-hand plane. But those don't, we're not graphing those right now. We're just talking about this bottom polynomial. And I just made this up to fill it out. So right here, we have 2 left-hand plane poles. Let's look at an unstable system example. Okay, I have G2 of S, and we're going to have this one, let's just have a number on the top, and then we'll have S minus 4, and we'll have 2 of them. Okay, so I know that I have 2 poles that are in the right-hand plane just by looking at this, because I'm looking at the bottom polynomial, and if we were to solve this, we have s minus 4 with a multiplicity of 2, so that equal to 0. So I have 2 lambda I at positive 4. So positive 4, positive 4. Both are in the right-hand plane. As we know from all of the classes previous, A pole or a system root in the right-hand plane implies instability. So that's just a real quick way to check the stability right there, and also what the poles and zeros are and where you can find them.